So, as I promised you, we had an exercise, and I'm not sure if some of you have in front of you the slides with the n-square matrix. I'm going to try to figure out how we can simultaneously see a couple of things here. So spare me 30 seconds. We are going to analyze briefly this example, and then we will have a few minutes to bridge from the systems architecture that we have been discussing to the software architecture that is the focus of the afternoon session. Okay, so, it's not blocking anything. So we have our 6 functions in our system, and these inputs and outputs represented in the n-square matrix. And we want to represent the functional flow of the system. So how do we represent a functional flow? With a which diagram? Activity diagram. How do we start an activity diagram? Black dot. Nice. So now we change our color frame. So what you may perceive as white is actually a black dot. Can I actually, I'm not going to bother changing the background, so bear with me. So we start, right? And we have our functions that probably will be actions there. So we have F0, of course.
What is the first function in the diagonal that you put here? The first. What is the criteria? The criteria is select a function that has only inputs from the outside. If a function has input from another function, it cannot be the first one. To be the first one, you have to have inputs only from the outside. F0 is a candidate. These are rules, very guidelines. Important, not mandatory, but help engineer. If 0 only has one input, mission command. So F0 input from the outside. F0 is candidate to be the first. Okay? If you have a function in the diagonal that is candidate to be the first, you can also translate it to the upper side. You can move all this diagonal, okay? With a tool, this is possible. You can move the functions in the diagonal.
That's a very good tip, Jose Luis. And actually, we can see that, yeah. So F0 is a candidate to be the first call, basically, the first step. We need to reach the end of the activity, and we need to execute all these functions along the way. As I mentioned before, this was a tricky example because these type of systems are highly parallel. So if we have a parallel system, that means we need a fork node. So we split the token into multiple for the different parallel functions that need to happen simultaneously. Now, we have no time to explain all this, so I'm going to start asking you, how do you think this should flow, basically? So F0 is getting the mission command. Let's just assume that this goes next, right? So if we split, we don't know where the other flow is going yet. So we execute this one. Remember, we are not representing here the items that are being exchanged. We are representing the flow of control. So now this one gets to work, to execute. So we have another function that we call localize pipeline, and it's taking as input the output of F0. So what shall I draw? Nice. Because probably it will execute next using that output, right? Now we have guide AUV, which is using a signal from localized pipeline and nothing else. So if we follow the diagram, we will execute it next, right? And it's producing a trajectory that is consumed by control AUV motion. But if you think now of what's being executed, so controlling the AUV is probably something that you need to be doing at all times, because you want to have control of what the AUV is doing at every control cycle. So as fast as you can, probably, or as fast as you need, better. So even if this is using, and actually you can see that there is a loop here. So if you go in detailed design, probably you will end up with also a loop here, okay? But at the level that we are representing now, probably this is going to be parallel execution with a change of data. So I'm going to go just faster with which things need to be happening all the time, because probably those are going to be separate parallel threads. So we have F6 as a candidate parallel thread. Inspect pipeline. This is interesting. So we can inspect if we are following, but we are inspecting in parallel to follow the pipeline. Because if we follow the pipeline, and then we decide, now I want to inspect it. It's why I was following it in the first place. Now I need to repeat. So see the trick here? There is a lot of parallelism here. So we know from that inspect pipeline and guide AUV, who is responsible for following the pipeline, are probably in parallel. So those are F2 and F5. And that's where you want to start reordering, so this doesn't get so messy. So we move F5 closer to F2 to make it parallel. And if they go in parallel, what do we need? A fork. I'm going to draw it this way. So they execute in parallel. So we have moved F3 somewhere here. What is F3 actually? Is localize the AUV, and that's probably also something that you want to continuously have. Your state estimation. Same as the control, the state estimation, that's running all the time, right? So that's a candidate to be running all the time. And what is F4 that doesn't have an input yet? That's monitoring the environment for obstacles, etc. Probably we also want that to be running continuously in a cycle, right? So these three functions are running all the time, and you can create a condition to decide when to stop that loop. But they run in parallel. This is a possible design. There is no right or wrong, so there is not an answer or the answer. There are multiple answers that may are good or bad designs, basically. So having these three in parallel, if you think of it, these are kind of autonomy-related capabilities. Being able to localize yourself, to move, and to observe the environment are closely related high-level functions to autonomy. And typically, those related to autonomy, they run all the time and in parallel to each other. But we also need to reach here so we can decide to have another thread, so when everything starts, we start also these basic capabilities there. And sorry, I am missing this one. This is a condition, for example, if not finished, well, yep. And for example, we could actually end this flow here or decide to merge. So if our mission finish, we just kill this control loop, basically. Sorry, control flow. Now, we are inspecting and we are following the pipeline, and we also want to finish simultaneously. So if there was a fork, we need a merge. And we could finalize the operation. A possible design. Maybe not the best one, but a potential design.
Is it necessary or possible to capture the need for parallelism in the requirements?
That's a very good question. So I don't know at which level would you treat the need for parallelism in the threads, in the functional flows.
Here, you are not in the domain of the solution. You are modeling the behavior you want. So, is the behavior you want? Perhaps parallelism depends on two things. If you have resources to run the things in parallel, the functionality, and also if there are no dependencies. So these two things, criteria, have to be used to parallelize. If you have dependence, for example, these two ones have a dependence. They cannot be parallel. If they don't have out-in dependence, you can parallelize. If you have resources to parallelize. So it's a mix of these criteria and the physical resources.
Actually, that's a very good point, Jose Luis. So maybe I said it wrong. Parallelism is the solution, so one possible solution. The requirement is how often do you need to control the motion? How often do you need to move? And depending on how that goes, maybe you cannot close a loop here fast enough, so you just run them in parallel, for example. Again, it's also a matter of level of abstraction. Here we are at a very abstract level. You can expect that the control motion function will have multiple sub-functions, and some of them will be creating some of the outputs that are needed, for example, for localization. So eventually the motion command will be used for localization. We are not depicting that in this diagram. We are still at a very high level of abstraction. And sometimes in these kinds of systems, I personally find it myself more complex to draw this more abstract one than when you go really into the inputs and outputs of the specific components. Then it becomes more clear. But if you, and that's the bottom-up approach, if you start from there, and then you start creating these abstractions, you start creating reusable designs for the different functions, basically. And that's why we explain this linearly from top down, but engineering process is iterations and refinement. And your architecture will change with those iterations and refinement. Oh yeah, sorry.
So do you not need to capture, if you go back to the last slide, not capture all like dependencies? Because for example, like I think it was F6, it was like F6 is dependent on F2, right? But it's now not captured in this one, right?
It's not captured. That's why modeling these systems is quite difficult because each using some output, but here we are not, this arrow is not the output. It's just the operation, the flow of control. So what will happen is that typically you have all these actives, and they are consuming some inputs and outputs from each other. You cannot see this here, and were able to draw this because I also know a lot about how this will eventually be input.
Okay, so you model something differently, kind of, or you only take part of the information there to put it in the action diagram.
So that's why these two views, even if related, the diagram and the n-squared chart are complementary. So you can get some input, so some ideas from the n-squared to come up with that one, but that doesn't mean that you can automatically generate this one from the other one. I'm using a lot more knowledge and information than just the n-squared.
In this case, that you have data is not so constrained parallelism as in the physical system. In a physical process, physical wall, not the cyber wall, the physical wall, you have a transformation. You are transforming dirty water in clean water. If a function depends on other function, they have to be in sequence in an industrial process. But in a cyber process, the dependency, if it has shared data, if you use a shared data as a dependency, you can be in parallel. So it's not so constraining as in the physical world. The outing dependency is more constraining in the physical world than in the cyber world. Here is that data world. In data
Okay, so apparently I can also pass slides on the Blackboard. So we have exactly 10 minutes to wrap this up, plus explain the software architecture. So I'm going to just give some hints and tips on it. First of all, you can check in the slides that we share with you a proposed solution. And please send me any comments, questions like, hey, this is wrong. No, this is not how we do it in our AUV. Please let me know. And we start changing our architecture for the REMARO AUV. We already discussed that there was a trade-off in between the inputs and outputs that you see in the n-squared matrix and the parallelism of this kind of system. This is just the description of what happens basically in the. So we had some conclusions that I think Jose Luis remarked through the presentation. So all models are wrong. We cannot model the wall precisely. That the best model is the wall itself, but they are useful. So please model for some reason. There needs to be a use for your model, and we have discussed the need for covering the scope. And address fidelity only to the required level, and how you can do this with our methodology. And one important aspect of our methodology is that it allows for bridging the system architecture with the software architecture. And now we are going to give you a snapshot of 7 minutes of software architecting with our method, because Ivano afterwards is going to explain you in detail about software architecting for robotic systems. So, Jose Luis, this one is yours.
You have to bridge the physical world, systems engineering is in the physical world, to the software world. That are two worlds that are different, because in the physical world, you have to respect the laws of conservation of mass and energy, and you cannot create and destroy things. Okay? But in the software world, you can create and destroy components. So both worlds are different. We have to bridge both worlds. The bridge is what we call the domain model. So, in the software world, we have components, we have frameworks. I recommend you a web page about all the software architectural frameworks based on ISO standard. The ISO standard describing software architectures. There is a web page, very interesting, of all the architectural frameworks. One of the frameworks is ppoa, it's my thesis. It's more than 30 years old. ppoa has, a framework has building elements, as ROS. You have a robotic framework that is called ROS. I have a framework that is called ppoa. We have components and coordination mechanisms. Components are typical software components. Domain components that are passive components. A structure, a list of things, of descriptions, or we have active components. Active components are process, a periodic or periodic processes, and controller. Controller is a component that is an asynchronous event controller. It's a component that receives events and handles the events, dispatching some process. It's a very complex component. These components were implemented in Java and Ada, in avionics, okay? Because I work in the area of avionics. Also, as we have different threads of execution, we need to coordinate in the system multiple threads of execution. For that, we need what we call coordination mechanisms. For example, semaphores, mutexes. You know, real-time operating systems, you work, mutexes, semaphores, buffers. Buffers is for communication. A semaphore or mutex is for synchronization of threads. So we need these building blocks. It depends on the kind of architecture. It's for real-time systems. Real-time embedded systems, monoprocessor. If you are in multi-core, that is the current issue right now, the coordination mechanisms are new. For example, the spin lock. You have different coordination mechanisms in multi-core architectures. Right now, in avionics, they are using multi-core, okay? But the main important here is this. We need to bridge a functional architecture for a system that is a physical system. Part of this functionality is implemented by software and how we implement it. Because in software, we don't use the concept of function, we use the concept of object, okay? Well, we build a domain model using a paradigm that is responsibility-driven modeling. Some of you know what is responsibility-driven modeling? The thing is, the objects have responsibilities. A class in a model, a class in UML has responsibilities. What is a responsibility? What the class has to do or what the class has to know. What has to do is implemented by operations or methods. What has to know? The attributes. You follow me? So, responsibilities are attributes are implemented as attributes or as operations or methods. So the important thing here, we are at a higher level of abstraction. So the important thing for us is identify from the functions that we will implement by software, convert, transform these functions into responsibilities of classes of analysis. This is what we call the domain model. We have
maybe I can jump into the example, basically. Yeah? So on a practical level, recipes, clear connection. So we need to create the domain model for the software subsystem, right? And Jose Luis was mentioning that you depart from the functions that you define in your system, and we are back to the collaborative robot. So these were the functions for the entire system, coming from systems engineering, our functional architecture. And some of these functions are allocated to the control software. So we identify those. And to obtain our domain model, we look for nouns. Nouns in the definition of those functions. And those nouns become the entities in our domain model, because that's what our software needs to represent, needs to manage, basically. So if we have an operator interface, well, maybe that's a potential class in our domain model. If we need to manage an order, maybe the order is something we need to represent. And this is basic object-oriented programming, right? If you are going to be managing customer orders, then you need to represent the order. That's one class in your domain, right? So this is exactly what we do. And this is a very practical, simple recipe on how you start obtaining your domain model, by identifying nouns in the description of your functions. So after doing that, we have more information. We look back also to the description for looking for verbs, and those represent the relationship between classes in our domain model. So I'm cheating, I'm jumping. This is the domain model for the collaborative robot. So we see that there is a class to represent the connection to the hardware. That's another trick. Almost every driver will be a class in your domain that is abstracting the hardware and allowing the software to manage the hardware, basically. So we have a robot skin driver, but we have also a driver indicated by the eye for the gripper, etc. We have an order that is made out of products. So this is our domain model, by identifying nouns and verbs in our functional description. So this is how we start bridging, moving from systems into software architecting.
Only one comment, Carlos. A typical mistake that my students and also engineers have is only model abstract physical things. No. You have also to abstract things as orders or events. So the abstraction in the model is not only the abstraction of the physical world. The abstraction is also the abstraction of events, transactions, places, etc. And it's very difficult for the students, typically, the domain model of a bank, only the physical things. No. Okay? In software, we are not working only with physical things. We are working with events, orders, descriptions, transactions, etc. There are good books about that. If you want, send to me an email, and I will recommend you good books about domain modeling. Okay?
Here is a concrete example of what Jose Luis was mentioning. We don't need to model the obstacle, really. What we need to model is that we detect an obstacle. So that's an event that relates, in this case, the coordinator that is responsible for coordinating the execution of the different operations in the robot, with the skin, who is responsible for generating the event, is the one detecting the obstacle. And so we complement this by assigning, as Jose Luis was mentioning, responsibilities to each class in the domain. And those relate directly also to the sub-functions that were needed from the functional architecture, and that we start allocating already by assigning them as responsibilities for our classes in the domain. So how do we move from classes in our domain model into the concrete software architecture made out of components? So there is a lot of magic there. Ivano will discuss tactics. We call them heuristics, but those are the same things. So we move from the domain model into the components and how the components execute, using, again, activity diagrams, by using architectural tactics. A couple of examples of those. So, for example, we have an heuristic on safety to avoid non-deterministic behavior. This is actually quite important in And it's also a challenge in autonomous systems, right? Because most of the algorithms that we use are non-deterministic for planning, etc. So how do we deal with this if we want to avoid such behavior? So in our case, for the robot that was picking things, the robot does not need to plan online every trajectory, because there is some structure present in the environment, and in the task, some of the trajectories can actually be pre-computed, because they will be the same always. So to approach one of the stacks of products, that's always the same trajectory. If we are certain that there will be no obstacles in that part of the environment, we can have pre-computed trajectories. So we avoid online planning and avoid non-deterministic behavior. So in this case, and in many cases, we use a trajectory database. We don't plan the trajectories. We plan them offline, we check that they were valid, and so we use them. And this is used way more often than you think. Robots are normally executing what they were told to before to ensure that nothing unexpected would happen. Even if in another system way more advanced that we developed, winning the Amazon Picking Challenge, we again use pre-recorded trajectories for most part of the motions, actually. Of course, you think that, oh, it's coming up with some nice trajectories, because part of that, the end of that trajectory, that was computed online, because it required to move in an unstructured environment that you could not predict in advance. But this heuristic for safety has a counterpart, so this relates to the structure of our system. So we need a database for trajectories. But does this need for safety affect also the behavior of the system? Yes, we already discussed about interrupting the motion, right? When there was an obstacle. So our robot was not being able to interrupt its operation at any point, only in this region. Why? Because there was one area in which the robot could interact with the people around, and there could be collisions. In the other part, at the back, the robot was moving in a perfectly defined environment where the human could not reach. So we could use predefined motions, blah, 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 there. But while it was interacting or moving in the part next to the human, we were allowing the skin to interrupt the motion, basically. So we limit the interruptibility region, not to the entire diagram, but only to this part. And this simplifies a lot the, or guarantees the design in the rest of the system. So the algorithms that we use in, that we develop, AI-based, online planning, etc., they are very useful. We need to identify where do we need them and what for, and limit the scope so as to ensure that the entire system performs as we need. That's why we need not only algorithm development, but systems engineering to get an entire robotic system to perform as expected. That's how we bridge from the system requirements, function architecture, into concrete case examples of architecting our system. And this will be the focus of the next talk by Ivano. And with this, Jose Luis and myself, we conclude for the day. If we can take maybe one question, but we will be available for more questions afterwards. But we need to move. So if there is a quick question, then I think we better move so that we are not late on schedule. Thank you.